White holes are curious mathematical opposites of black holes. And they were discovered mathematically in, I think it was the early 1970s, when black hole mathematics was maturing. You have the idea, how do you make it work? You go through the equations, bada bing, here's this black hole. It works. It's predicted by Einstein's relativity. He didn't predict it. He didn't keep using his own theories and equations. He did not go there because it was too extreme even for Einstein to reach. We land there in the early 1970s, late 1960s. Here's a black hole, a region of space, nothing comes out ever. It's a collapsed region of space-time. And we have evidence for them in the centers of galaxies as endpoints of the death of stars. At the time, you realize you can take the equations that give you a black hole, and you realize, it turns out, there's another solution to those equations. It's not that complicated to imagine. If I take the number 9 and I ask you what's the square root of 9, what would you tell me? And you'd say 3. Because 3 times 3 is 9. So 3 squared is 9. Square root of 9 is 3. So we got that, okay? So the answer to the question, what is the square root of 9, is 3. However, I now ask you, what is -3 times -3? It's also 9. So in fact, the answer to the question, what is the square root of 9, has 2 solutions, 3 and -3. They're both legitimate solutions to that question. One is not more better than the other. The equations that give you a black hole, there's a second solution to it. It's the mathematical opposite of the black hole, where everything only ever comes out of it. What possible other word would we pick for this? A white hole. Early 70s, people said, all right, we got this. What would a white hole look like? Is there evidence for one in the universe? So we trained the telescopes on the universe. Found none. So right now, white holes are in the repository of science fiction ideas that you might want to do something with or not. But there's no evidence for them as being real objects in our known universe.
Okay, let me get this out of the way. White holes are almost definitely not a real thing that can be found in nature. So keep that in mind when I say we might have seen one. White holes only exist in math, but in 2006 we saw an explosion of light out in deep space that we can't explain any other way. Detected by NASA's SWIFT satellite on June 14th, it was a huge gamma ray burst, the highest energy type of explosion possible, 1,000,000 trillion times more energetic than the sun. And it lasted for 102 seconds. Scientists believe that gamma ray bursts only last that long during supernovas. But this one, labeled GRB 060614, didn't have a supernova to go with it. As far as we can tell, it was an explosion of white-hot light that came from nowhere and then vanished. And while white holes remain incredibly, stupendously, ridiculously unlikely, that's pretty much exactly what we think one would look like. Some physicists have offered other explanations for what it might have been, like a shockwave from a neutron star torn apart by a black hole, or maybe 2 neutron stars colliding. But events like these only release energy for 2 seconds at most, not a minute and a half. So, white holes in nature are as impossible as a thing can be, while still being technically possible. But they are technically possible. And until we see another explosion like the one in 2006 that we could hopefully learn more from, we'll just have to wait and wonder.
There are 2 competing explanations to describe black holes. One of them is Einstein's theory of general relativity, where the mass of a black hole bends space-time so much that it becomes one single point of infinite density. On the other hand, according to quantum mechanics, there can't be an infinitely small point. It can be very, very small, but not infinitely so. And this irreconcilable difference is one of the greatest debates in physics, since general relativity is our best description of gravity, while quantum mechanics has been called the most successful theory ever. But some physicists believe white holes could square these two predictions and reveal what's happening inside a black hole. The equations of general relativity allow for the possibility of white holes. All you have to do is set the mass of the singularity to 0, and everything gets turned on its ear. Instead of a cosmic vacuum cleaner that sucks everything up that strays too close, you get a whatever the opposite of a vacuum is. I'm not good with metaphors. But the point is, all it can do is just spew stuff out. But then the question is, how do you get a singularity, a point of infinite density, remember, with no mass? And how does a massless singularity spit anything out? Because of that head scratcher, white holes have long been written off as a mathematical quirk, but not something that can happen in reality. However, quantum mechanics allows for some adjustments to the solutions of the equations of general relativity. And with those adjustments, the interior of a black hole could transform into a white hole. One physicist describes it as though the curved space-time of the black hole itself is bouncing out again, and this rebound opens up some tantalizing possibilities. Since a black hole might transform into a white hole, that means things falling into it may come out again. This would solve another issue quantum physics has with black holes, because in quantum physics, information cannot be destroyed. Granted, whatever came out of a white hole would be a very mangled version of its former self, but nonetheless, information about what it was would not be deleted from the universe. It sounds like a wormhole, but instead of traveling through space, the object would travel through time. Small black holes that formed just after the chaos of the Big Bang may have already converted. They would be invisible because they'd be smaller than the wavelength of light, but have the mass of about 1/1,000,000th of a gram. White hole proponents say this could make them an attractive candidate for dark matter. Yeah, the upsides of white holes just keep getting better and better.
We actually did talk about a case where a random drop in entropy led to something very much like a white hole in this episode. It's been speculated that the Big Bang itself came from such a profoundly improbable entropy dip. And as it happens, the Big Bang looks, mathematically at least, much like a white hole. It's an expanding outpouring of space-time containing a vast amount of energy, and the bang itself can never be entered. After all, it's in the past. The difference between the Big Bang and a white hole is that the former possesses no singularity. It happened everywhere at the same time. Still, that hasn't stopped physicists from having fun with the idea. It's been proposed that when a black hole forms, a white hole forms on the opposite side. Energy entering the black hole exits the white hole. Physicist Lee Smolin takes it a step further to suggest that the resulting white hole is the Big Bang of a new baby universe, and that in fact our universe formed that way. More on that another time.